Welcome to the Deep Dive. This is where we take sources suggested by you, our listeners. Today, it's a really fascinating study, and we pull out the key insights.
That's right. And today we're tackling a really important one. It's called the mutual dependence of negative emission technologies and energy systems.
Quite a title, but it gets right to the point.
It really does.
Mhm.
The study looks at a core challenge for hitting our climate goals. I mean, we all know cutting fossil fuels is absolutely vital, right?
Right.
But this research, it really underlines something else. We're probably going to need negative emission technologies, or nets, to actively pull CO2 out of the air.
Yeah, to actually keep warming well below that critical 2 degree Celsius mark.
Exactly.
And what I think is so valuable about the mutual dependence of negative emission technologies and energy systems is how it zooms in on something that, well, maybe gets overlooked sometimes. The energy side of deploying these nets.
Yeah, absolutely. It's not just can we capture CO2, but how do these things actually plug into our future energy grid? How much power do they need, or maybe even produce?
Precisely. So that's our goal today, to really dig into how different nets, based on this study, might integrate, the energy needed per ton of carbon, the whole picture.
And to frame that, the mutual dependence of negative emission technologies and energy systems mainly focuses on two big players. Bioenergy with carbon capture and storage, that's BECCS,
Got it.
and direct air carbon capture and storage, or DACCS. So we'll be exploring both of those as we go through the study's findings.
Okay, great. So let's start with why we even need these nets in the first place. The mutual dependence of negative emission technologies and energy systems seems pretty clear on this.
Yeah, it is. Basically, most climate stabilization scenarios, even the really ambitious ones, aiming for 1.5 degrees, they don't just bank on emission cuts alone.
Right. They sort of assume we'll also need this carbon removal component.
Exactly. The scale is it's huge. This study reminds us that even with pretty drastic emission cuts by, say, 2050, we might still need to remove billions of tons of CO2 from the atmosphere every year.
Billions. Wow. That really puts it in perspective. It's a fundamental shift, isn't it?
It really is. And it makes you think about, where the investment is going. We're pouring money into renewables. Obviously, that's crucial for replacing fossil
It
fuels.
has to happen.
But this study argues we need parallel investment in these nets now because innovation takes time. Scaling up takes time. Decades, potentially.
Well, we can't just wait until 2050 and then go, okay, now let's figure out carbon removal, right? The mutual dependence of negative emission technologies and energy systems says that's too late.
Precisely. It's got to be a two-pronged approach happening simultaneously. Okay, so let's get into the first of those big nets the study looks at. BCCS, bioenergy with carbon capture and storage. How does that work in simple terms?
So BECCS, as the study lays it out, basically uses biomass, stuff like wood chips, crop residues, that kind of thing, as fuel. You burn it to generate energy, maybe electricity, maybe biofuels, maybe even hydrogen. But the key part is the CO2 that's released when you burn it. You capture that and store it underground usually. The idea being the plants sucked up CO2 while growing, so the whole process can be carbon negative.
Right. And the mutual dependence of negative emission technologies and energy systems talks about the potential scale here. Some scenarios see BECCS playing a really big role.
How big?
Well, we're talking potentially 190 to 300 exajoules of biomass energy per year by 2050 in some scenarios.
Yeah.
Maybe even higher for the 1.5 degree pathways. An exajoule is, well, it's a massive amount of energy.
Okay, but here's the catch, isn't it? And the study points this out quite strongly. All that biomass needs land. A lot of land.
That's the big concern.
The mutual dependence of negative emission technologies and energy systems really flags these huge land requirements. And that brings up tricky questions, right? Like competition with food production, could it drive up food prices?
Yeah.
And what about the environmental impacts? Water use, biodiversity, land degradation. It's complex.
It really is.
Yeah.
BECCS offers this potential for carbon negative energy, but scaling it up to the levels some models suggest, well, it raises serious sustainability flags, as this study makes very clear.
Though it's worth noting the study does mention some scenarios project lower bioenergy use too. So it's not a completely settled picture, maybe.
No, definitely not. The exact scale is still debated in the modeling world. Okay, let's pivot to the other main technology and the mutual dependence of negative emission technologies and energy systems. DECCS, direct air carbon capture and storage. This one sounds a bit more sci-fi.
A little bit, yeah. So DCCS, as the study describes it, basically uses chemical processes to grab CO2 straight out of the ambient air, like giant air filters, but just for CO2.
And then, same deal, the captured CO2 gets stored underground.
Okay, but filtering the whole atmosphere, that sounds like it must take a lot of energy itself, right?
Bingo. That's the key challenge highlighted in the mutual dependence of negative emission technologies and energy systems. DCCS has potentially very high energy demands.
How high are we talking?
Well, some scenarios in the study projects, it could eat up maybe 12% of global electricity and even up to 60% of non-electric energy by 2100. That's substantial.
Wow, 60% of non-electric energy.
Yeah. So where that energy comes from is absolutely critical, as the study stresses.
Okay, so on the flip side, though, the mutual dependence of negative emission technologies and energy systems notes that DCCS might be more flexible location-wise. You could put plants near cheap renewables or near storage sites, maybe.
That's an advantage, yes. And potentially a lower direct environmental footprint compared to the land needed for BECCS. Though the study is careful to mention there are still research gaps on potential DACCS side effects, too.
And it definitely needs much less land, right? That seems like a huge difference.
Oh, massively less land for the capture part itself. But, and this is the crucial but in this study, the overall environmental impact hinges completely on the energy source, powering DOCCS with coal. Not much point, is there?
Right, you'd just be shuffling emissions around. This leads us nicely into the study's discussion on energy requirements and efficiency. They talk about energy per carbon metrics.
Yeah, basically how much primary energy input do you need to sequester 1 ton of CO2? It's a key efficiency measure.
And what's the verdict according to the mutual dependence of negative emission technologies and energy systems, DCCS versus BCCS?
Well, interestingly, the study finds that DCCS actually requires less primary energy per ton of CO2 sequestered compared to BCCS.
Really? That seems counterintuitive, given you just said DCCS needs so much energy overall.
I know, it sounds odd at first. Yeah. But it's about the energy per ton removed. The study digs into the numbers. For DCCS, there's a range depending on the specific tech. Liquid sorbents often need high heat, so their energy input can be higher. But the study highlights newer assessments of solid sorbent DACCS, which can run at lower temperatures. These look, well, energetically better. The paper gives some lower ranges for those. It even compares current tech to the absolute theoretical minimum energy needed, just to show how much room for improvement there might still be.
So the specific flavor of DACCS really matters, it sounds like. And the mutual dependence of negative emission technologies and energy systems suggests these low-temp versions could pair well with renewables, like using heat pumps or solar thermal.
Exactly. The study mentions looking at it through an exergy lens, basically, the quality or usefulness of the energy. Using low-grade heat efficiently is key.
So maybe solar PV powering heat pumps for a DACCS unit? That could work?
The study cites modeling suggesting just that, yeah. Could be quite economical in sunny spots.
Okay, and what about BECCS on this energy per ton metric? How does it look in the mutual dependence of negative emission technologies and energy systems?
Well, the study notes that the big climate models, the integrated assessment models, or IAMs, typically estimate around 14 gigajoules of primary biomass energy per ton of CO2 captured for BCCS. There's a range, of course.
But I sense a but coming.
You're right. The study raises a really important point. Those models might be overestimating the net energy yield from BCCS. They might not fully account for all the energy needed upstream, growing, harvesting, transporting the biomass.
Ah, right. The whole life cycle energy cost. That makes sense. It's not free energy just because it grew.
Exactly. And the study even hints that, conversely, some models might be overestimating DACCS energy needs based on some newer industrial data for solid sorbents. So these numbers are still evolving.
Lots of moving parts. Okay, let's move to another really critical concept in the study, net avoided carbon, or sequestration efficiency.
Right, because capturing a ton of CO2 doesn't help much if you emitted almost a ton of CO2 generating the energy to capture it.
Exactly. So the study talks about this benchmark study on DACCS, the APS one, using liquid sorbents.
Yes, that's a good example they cite. It looked at a DACCS plant powered by fairly carbon-intensive grid electricity, but using natural gas for heat, albeit with carbon capture on the gas combustion.
Okay, so even capturing the CO2 from the heating fuel.
Right. Even doing that, the net CO2 removed from the atmosphere was only about 70% of what the DACCS unit initially pulled from the air. The rest was basically offset by the grid emissions.
It really drives home how vital low-carbon energy is for DCCS. A point the mutual dependence of negative emission technologies and energy systems hammers home.
And this study itself ran some scenarios A, B, and C looking at exactly that, right? Different speeds of decarbonizing the energy system.
Yes, and the results were stark, according to the paper. The faster you decarbonize the electricity and heat supply, the more effective DACCS becomes at actual net carbon removal.
Makes sense. If the energy grid stays dirty, DACCS doesn't achieve nearly as much net benefit. Precisely. A crucial finding from the mutual dependence of negative emission technologies and energy systems. They also looked at a specific scenario with solid sorbent DACCS, powered purely by PV and geothermal.
And how did that look, efficiency-wise?
The study estimates the net CO2 equivalent emissions were pretty low in that case, relative to the CO2 captured. It shows the potential when you pair it with clean energy.
Okay, so how does BECCS compare on this sequestration efficiency metric according to the mutual dependence of negative emission technologies and energy systems?
Well, the study reports a range, but notes that in some cases the net emissions from the process itself could be like 10 to 50% of the CO2 captured. And that's before you even consider indirect land use change.
Ah, the land use a ghost again. So if growing biomass pushes farming onto, say, deforested land.
Exactly. Then the actual net benefit of BCCS could plummet or even disappear. That's a huge uncertainty the study points out.
So, bottom line from the study seems to be, DACCS generally offers higher, more reliable sequestration efficiency, maybe 75 to 100%, whereas BACCS is more like 50 to 90%, and potentially much lower depending on land use factors.
That's the conclusion, yes. A significant difference when you're talking about verifiable carbon removal.
Which leads us to costs and accountability, I guess.
Exactly. And the study is clear. We'll need some form of carbon pricing to make any of these nets fly at scale.
Makes sense. So, cost-wise, where are we now, according to the mutual dependence of negative emission technologies and energy systems?
Currently, the study cites estimates for BACCS around, say, $100 to $200 per ton of CO2. DACCS is generally seen as more expensive today, maybe $100 to $300 per ton, sometimes higher.
So BCCS looks cheaper on paper right now.
Right. And that's probably why it features so heavily in many climate models, as the study suggests.
But the study thinks that might change, especially for DACCS.
Exactly. DACCS is more like a manufactured technology. It's modular, you can build lots of units. That means there's huge potential for costs to come down through learning by doing, innovation, mass production.
Think solar panels, right?
Yeah, okay. Yeah. Good analogy. Whereas BECCS relies on large, bespoke power plants and, crucially, on growing biomass. There are limits to how much you can reduce the cost of farming and logging, especially when land gets scarce. That's a key point in the mutual dependence of negative emission technologies and energy systems. And the land difference is just staggering, isn't it? Remind us of those figures from the study. Yeah, it's dramatic. To remove 10 gigatons of CO2 a year, which is the kind of scale we might need, the study estimates DACCS might need about 1 million hectares for the actual air contactors, BCCS. Could be anywhere from 400 million to 2,400 million hectares.
Mind-blowing. Hundreds or thousands of times more land for BCCS.
Yeah. And as land gets tighter, the cost of that biomass for BCCS is likely to go up and up. The study argues this could really erode that initial cost advantage. Plus, there might just be a limit to how much biomass you can source sustainably, capping BECCS potential overall.
Which brings us back to that accountability point you mentioned. How does the mutual dependence of negative emission technologies and energy systems see that playing out for investors?
Well, for investors putting money into carbon removal, they need to be sure the carbon is actually being removed and staying removed.
Makes sense.
DCCS has a big advantage here, the study explains. You capture the CO2 right there at the plant. You measure it, you inject it underground. It's relatively straightforward to track and verify.
Okay. And BCCS?
Much trickier. You've got the whole complex life cycle of the biomass, where it was grown, how it was managed, did it cause indirect land use change. It's much harder to pin down a definitive, uncontested number for net CO2 removal. This uncertainty affects its value in carbon markets, a really important point in the study.
So DCCS potentially offers more transparency, more certainty for investors.
That seems to be the implication from the study, yes. Now, to give a feel for how things can play out, the mutual dependence of negative emission technologies and energy systems sketches out 4 qualitative future stories.
Yeah, the scenarios. What were they?
2 for BCS, 2 for DCS.
Okay, for BCS.
There's the yield story. Basically, we get really good at growing biomass efficiently, high yields, less land needed, so BCCS scales up without causing too many problems.
the optimistic BACS future.
Right. Then there's the land story.
Hmm.
Intense competition for land with food, biodiversity, etc., which limits how much BCS we can do and makes it more expensive. Both outlined in the study.
Got it. And for DCCS, the study outlined
An energy story. Innovation is slow, DCCS stays energy hungry and expensive, not great.
the pessimistic DCCS path.
And then the innovation story.
Yeah.
Breakthroughs happen, DCCS gets cheaper, needs less energy, integrates really well with cheap renewables. That's the positive outlook for the DCS presented in this study.
So these stories really just frame the uncertainties, the different ways things could unfold depending on tech progress, resource constraints.
Exactly. It emphasizes that the future isn't predetermined for either technology. Which brings us to the final big theme in the mutual dependence of negative emission technologies and energy systems. The implications for power systems. How does the speed of decarbonizing our energy grid affect nets?
Yeah, that connection seems crucial.
Well, the study makes an interesting point. If we decarbonize slowly, we actually need more nets to hit our climate targets.
But those nets will be less effective because the energy powering them is still dirty.
Precisely. It's a bit of a paradox. Slower grid decarbonization makes nets more necessary but less efficient, especially early on. A key tension explored in this study.
Okay. And the study also looked at how these nets fit into the grid operationally, right? DACCS with high costs.
High capital costs, high energy costs. It really wants to run as much as possible, high utilization rates, ideally powered by cheap, low-carbon energy. So maybe baseload nuclear or geothermal or renewables paired with lots of storage.
Makes sense. And BECCS. How does it fit into a future grid potentially dominated by intermittent renewables, according to the mutual dependence of negative emission technologies and energy systems?
That could be challenging. If you're only running your expensive BECCS plant when the sun isn't shining or the wind isn't blowing, its utilization might be low, making it hard to pay back the investment. Plus, the study notes a trade-off within BECCS itself. Do you optimize it to generate the most electricity or to capture the most CO2? You can't always maximize both.
So maybe in a future with super cheap renewables everywhere, the energy part of BECCS becomes less important, and it just becomes about capturing the biomass carbon.
That's a really interesting potential evolution this study touches on, shifting from BECCS to BCCS, biomass carbon capture and storage, where energy generation isn't the primary goal.
Fascinating. So to wrap up, what does the mutual dependence of negative emission technologies and energy systems suggest for future research?
It really calls on the energy systems research community to dig deeper into how nets actually operate within different future energy systems. We need better models, more detail.
And key things to track.
The study highlights utilization rates, that sequestration efficiency we talked about, and reliability, all crucial for making these things economically viable and credible in carbon markets. They also float the idea of looking at synergies. Could BECS provide power for DACCS, or should we just treat them as separate things? Lots to explore there, as the study suggests.
Which all comes back to the title, doesn't it? The mutual dependence of negative emission technologies and energy systems. You can't really understand one without the other.
Exactly. That's the core message. The success of nets is totally intertwined with how our energy system evolves.
Okay, so let's try and summarize the key arguments from our deep dive into the mutual dependence of negative emission technologies and energy systems. It seems DACCS holds significant promise, especially if we decarbonize our energy fast. It needs less primary energy per ton removed, has higher, more reliable efficiency.
But its costs need to come way down through innovation. That's the big hurdle.
Right. While BECCS faces these really significant challenges around land use, sustainability, and just accounting for the carbon accurately.
And importantly, this study really pushes back on some assumptions in those big climate models, calling for much more detailed energy system-focused analysis of nets, as laid out so clearly in the mutual dependence of negative emission technologies and energy systems.
Absolutely. Well, this has been a really illuminating deep dive into the mutual dependence of negative emission technologies and energy systems. And it leaves us, and you listening, with a final thought to chew on. Given everything this study highlights, what does it mean for energy policy and investment going forward? Is betting heavily on BECCS still the right path? Or should the focus shift more towards accelerating DACCS innovation and integrating it with renewables? And just how big a role can innovation realistically play in shaping which path we ultimately take?
Lots to think about. We definitely recommend checking out the full study, The Mutual Dependence of Negative Emission Technologies and Energy Systems, if you want to go even deeper.
Definitely. Thanks for joining us on the Deep Dive.